we are showing impact extrusion in a different schematic diagram. I do that from time to time, that rather than having all the pictures or schematic diagrams from one book, I collect it from other books also, so that we can take a look at the same operation from different viewpoints. It makes it easier, right? So you have the die, you have the bottom die, right? And you have the blank material, which is in normal extrusion, this is called a billet material. And you have the top die, which is the punch, right? And here it is just an ejector pin. I'll tell you, it is just like you did in casting. So you come with a boom, right? One hammer blow. One hammer blow is there. This material goes outside, right? Round. So it becomes a round hollow piece. And then you pull this back up. So the ram or the punch goes back up. And now you use the knockout or the ejector pin so that this hollow piece goes out. So now it is back in the same position again. You put a new blank material and you do the process again. So it comes down with an impact load. It takes this shape. This punch goes back up and the produced part, the hollow part, is knocked out by the ejector pin. So this keeps on going on. Now to your favorite part, a little bit about the mathematics of extrusion. We have explained the basic process, right? I think in quite some detail, and we will have some more later on. A0 or A0 is the cross-sectional area of the billet, right? So the original material, which is in a cylindrical form, the original material. So the original material comes with an initial cross-sectional area. And after you finish extrusion, there is a cross-sectional area of the final product. So here we are calling that AF, area of the extruded product, cross-sectional area, of course, right? So cross-sectional area of the original billet is A0 and final cross-sectional area of the extruded product is AF. This ratio of A0 to AF is called extrusion ratio. This is a standard name. It is a very important thing which will be used a lot in calculations and so on. And it is called R, capital R. So capital R is the ratio of the original cross-sectional area of the billet to the final cross-sectional area of the extruded product. This is capital R. It is called extrusion ratio. Now, there can be hundreds and thousands of different dies of different shape and different things and so on. As an example, you know that in Rossel, just next to the university, the Rossel, there is a big industrial area. One of that companies is called NAPCO, National Aluminium Products Company, NAPCO. So they are a major extrusion plant. If the pandemic was not there and so on, then usually we take you as manufacturing students to 1 or 2 real plant visits for 2 to 3 hours and so on. And we show you the whole real process. So this NAPCO, the National Aluminium Products Company, which is a large extrusion plant, is one of the places where we generally take you. That NAPCO has about 10,000 different dies. 10,000 different dies. Each die is a different shape because different customers from around the world, from Oman, from the Gulf region and so on, can ask you for different types of shapes and so on, right? So therefore, from very simple solid rounds to solid hollow shapes to very complicated shapes, which he showed you earlier in slides. So it means that the dies can be of different complexity. Dies can be of different complexity. And if the die is more complex, it is intuitive. We expect that the extrusion will be very difficult. We will need more forces and there will be more chances of failure. So therefore, before we start to extrude in a new die, we want to find out how complex this shape is. So we define complexity by what is called a shape factor. This equation is called a shape factor, and this is one way of describing how complex your die is. So shape factor is the profile perimeter or the section perimeter. After extrusion, whatever shape you have, you take the perimeter, just the perimeter. If it is solid round, then this circumference is the perimeter, right? If it is a square, then the length of the square is the perimeter. So it is the profile or the section perimeter divided by the profile or the section area. So for example, if it is a round bar that we are extruding, the perimeter is 2 pi r, isn't it? The circumference of a round shape is 2 pi r. So the profile perimeter is 2 pi r, but profile area is pi r square, right? So this is it. This is by definition. If it is a square shape, then the perimeter is the sum of the 4 equal lengths, that is the perimeter, and the area is this length multiplied by this length, a square, right? So perimeter upon area of the final extruded shape, that is called the shape factor, and this gives you an idea of how complex the shape is. Okay, compare a solid cylinder. We just told you, solid cylinder, the perimeter is 2 pi r and the area is pi r square. Compare it to a gear. The inside of the gear is, say, solid, but the outside is cut into 20-30 different teeth. So the area is roughly the same area, but the perimeter, you go along each tooth, there are 20. So the perimeter is now very large. So the perimeter is very big, even though the inside area is roughly the same. So the ratio of the perimeter to area now will be a very big number, isn't it, compared to the other. So this is intuitive. This equation is there. But the first person who would have defined complexity of an extrusion die based on this would have been a brilliant person. That now, yes, I can see that if it is very complex shape, then the perimeter will be a very large number and the area will be a simple number, and so on. So this is one way of mathematically, quantitatively defining the complexity of the. We can just say this is very complex, this is medium complex, this is very simple, but that is not giving us a number. But this shape factor will give you an actual number, 1, 1.5, 2, 2.3, whatever. So now we can categorize different dies, extrusion dies, according to their complexity. Extrusion die features. So let us see again the simple diagram, that the material is coming from here. There is the ram which is applying pressure. This is the material. This is the die. You see, this is a round die, right? We are showing you a 2D view, but there is a round plate, a disc, in which the shape is cut. This shape can be a simple round, can be a hollow, can be a square, can be whatever, right? So we are showing you a 2D view, but this is a round disc. Similarly, this container is a round tube, inside which the cylindrical billet will come, isn't it? And so this is the die, and there will be die backers and so on, and the material, the billet material, will be pushed through it, and then it will take the shape of the die. Now this angle could be 90 degrees, but if it is not 90 degrees, right, if it is 90 degree, then the material will be completely pushed at the die, and once it cannot go further, then it will start to come down and come here, if it is a 90 degree, right? So the force will be very high. But if it is already a slope, the material will hit and then slide into the die, right? So this is the die angle alpha. Now inside the die also, this shape could be flat, or a slight clearance is there so that the material can flow more easily. So that will be a sort of a back angle, which we are not showing here, right? But this entrance angle can be there, and this entrance angle, if it is there, if it is not exactly 90 degrees, then it will make the flow of the material easier, right? So the die angle, if there is low die angle, the surface area is large, which increases the friction at the die billet interface. Now you see, the billet material is in contact with the container. That is the container billet interface. So that friction is between the container and the billet. But once the material hits the die, then the friction is between the die and the billet, right? So low die angle, the die billet interface friction will be high. So the ram force that we will have to apply will be a high force to overcome the higher friction. If there is a large die angle, then there can be a lot of turbulence in the metal flow. The metal is coming like this and then like this and then going out like this. So the metal is flowing, metal flow lines, just as we showed you in forging and so on, metal flow lines. So if the die angle is large, then there will be more turbulence in the metal flow. And because of this turbulence, there will be more ram force, right? So there is low die angle, force will be high because of friction. Large die angle, force will be high because of turbulence. So in between there should be some optimum. So the optimum angle depends on the billet material, the billet temperature, lubrication and so on. And here we will give equations later on, but using the equations, here is the ram force or the pressure, it depends. And here is the die angle. So if the die angle is a small, then this is a high pressure or high force required. If the die angle is very large, it will again be very high. And at some place it is optimum, it is minimum, right? So there is some optimum die angle at which the ram force or the ram pressure or the work required will be the lowest. For low die angle, it will be high because of friction. At high die angle, it will be high because of turbulence, the metal flow, isn't it? So this is a very beautiful diagram. This is based on the actual pressure equation or force equation, which we will show you later on. But here we are just trying to explain that the die angle is a very important parameter. Here we are showing you metal flow in extrusion, just like we were trying to do that in forging and so on. But this time the billet is there, the container is there, and it has to be forced so that it ultimately goes through the die. There is the die. So it will be ultimately forcing through the die, right? So there will be some friction here, but here at the back side it is more smooth. If friction is slightly higher, then right here there is almost no friction between the container and the billet. So it is flowing smoothly. Only when it changes the shape to enter the die, then some disturbance is there. Now here there is some friction between the container and the billet. So now because of the friction, it cannot be as smooth. Some disturbance is here also. And here there is a high friction between the billet and the container, high friction. So low friction, medium friction and high friction. But which friction? Not friction between the material and the die. That is a very small area. But the friction at the billet container interface, right? So a schematic illustration of three types of metal flow in direct extrusion. The die angle in these is 90 degrees. No friction at container billet, most homogeneous flow. Medium friction, there is a dead metal zone, and very high friction. The dead metal zone is very large, right? So some material does not flow, it gets stuck here. So this is called the dead metal zone. And this dead metal zone will be a medium size when the medium friction is there. It will be large size if large friction is there. And of course, if the friction is large or if the dead metal size is large, then the ram force or ram pressure that we need will be much larger.